The investigation into the loss of Lancaster ED-603 begins not with a military search but with an industrial accident. In March 1996, the commercial fishing cutter VD-64 was operating on the IJsselmeer near the Off-Sloat Dike, roughly 6 kilometers off Brayson Dike. The vessel was trawling for fish when its gear snagged on a submerged obstruction. The crew applied winching tension to free the net, expecting a rock or a discarded anchor. Instead, they brought a 12-cylinder Aero engine and, crucially, its identification plate up from the lake bed. The object was heavily corroded and caked in silt, but it remained recognizable as a Merlin 28, a Packard-built variant of the Rolls-Royce design. Recovery of anonymous aircraft debris is common in the former Zuiderzee, a part of the Netherlands where thousands of aircraft were lost during the Second World War, including several hundred over the Zuiderzee and IJsselmeer region. Most recovered components are unidentifiable scraps. This one came up with its serial plate still in place. The stamped serial number was the anchor proof needed to settle a question that had hung open for more than half a century. A check of the Royal Air Force loss records confirmed that this engine belonged to Lancaster ED-603, a Pathfinder aircraft from 83 Squadron. The bomber had been missing since the night of June 12 to 13, 1943. The surfacing of the engine converted a patch of empty water into a confirmed crash site, solving the location of the airframe but leaving the status of the crew unresolved. The identification of the wreckage triggered a controlled legal and administrative process that treats the site as a potential war grave. This designation is not merely commemorative, it places strict limits on access and disturbance. In the Netherlands, wreck sites that may contain missing aircrew are managed as protected locations under government oversight, with recovery permitted only through a mandated licensed operation. In practice, that means no recreational diving, no commercial salvage, and no unapproved interference with the sediment. The site becomes a controlled forensic zone coordinated through the National Program for the Recovery of Aircraft Wrecks. Despite the positive identification in 1996, no full recovery excavation was undertaken for another 27 years. This delay defines the difference between emergency rescue and survey-only aviation archaeology. The site posed no navigational hazard, and the depth of 13 feet protected the remains from casual interference. In 2023, the Netherlands finally opened the site under a national program aimed at cases with missing aircrew. The objective was specific. 4 of the 7 crew members had washed ashore in 1943. 3 men, Pilot Officer Arthur Smart, Pilot Officer Raymond Moore, and Pilot Officer Charles Sprack, remained unaccounted for. The working assumption was that they were still inside the fuselage, entombed in the clay beneath the engine retrieval point. Before any physical recovery could be attempted, the site required mapping. The primary tool for this survey is side-scan sonar. This system operates by towing a transducer fish through the water column at a fixed altitude above the lake bed. The device emits a fan-shaped pulse of acoustic energy, perpendicular to the path of travel. When this acoustic pulse strikes a hard object like an aluminum spar or a steel engine block, the sound wave reflects back to the sensor, registering as a high-intensity return on the display. Conversely, soft sediment absorbs the energy, appearing as a dark background. The geometry of the return also creates an acoustic shadow behind the object. By measuring the length of this shadow, engineers can calculate the height of the debris protruding from the mud. However, the survey of ED-603 revealed a critical limitation of acoustic mapping. The 1996 engine recovery had shown that the wreckage was not resting on the surface. It was buried. The high-energy impact had driven the heavy mechanical assemblies deep into the soft sediment of the lake bed. Side-scan sonar cannot penetrate the subsurface. It can only map the protrusion. The acoustic data showed a debris field, but it could not confirm the integrity of the fuselage or the location of the crew stations. The scan confirmed only that a significant anomaly existed at the coordinates derived from the fishing boat snag. 80 years separate the loss from the mobilization in 2023. In that time, the aircraft transitioned from a weapon of war to a missing asset, then to a snag hazard, and finally to a protected archaeological target. Once the state committed, the mission narrowed to one measurable outcome. The goal is to verify the identity of the 3 missing airmen and return them to the surface. The Royal Netherlands Air Force and the contractor Leemans Speciaalwerken already had the point in the lake. What they did not have was access. To recover the evidence with the necessary forensic precision, the engineers could not work underwater. They would have to remove the lake from the equation. At 2:11 in the morning on June 13, 1943, the operational clock for Lancaster ED-603 stopped. The bomber was returning from a raid on Bochum, flying through the dark over the Netherlands. It was intercepted by a Luftwaffe night fighter flown by the German night fighter pilot Rudolf Siegmund. The engagement was brief. The Lancaster was hit, lost control, and came down into the IJsselmeer. Some accounts describe an attempted emergency water landing that ended with the aircraft flipping inverted. Others frame it as a hard, uncontrolled impact. Either way, decades later, the recovery team confronted the same reality. The wreck was buried, not displayed on the bottom. For a recovery engineer, the key variable is not the label, ditching versus impact, but what the water and the shallow depth do to a large aircraft in its final seconds. In the best-case ditching, a crew tries to settle the aircraft onto the surface long enough to escape. In a hard entry, water can behave like a solid barrier, and the structure can fail at joints and stress points, separating major sections. In the IJsselmeer's shallow water, the heavy components, engines, landing gear, and main structural members, can retain enough momentum to punch into the saturated sediment, leaving the evidence locked below the lake bed. This mechanism explains the distribution of the crew. 7 airmen were on board when the aircraft departed England. Following the crash in 1943, the bodies of 4 crew members washed ashore or were recovered from the surface waters. These men were likely thrown clear during the initial breakup or were in sections of the fuselage that disintegrated on impact. However, the remaining 3 crew members vanished. The recovery logic posits that these men were at stations inside the fuselage sections that remained intact enough to trap them and heavy enough to drive into the clay. They did not float because they were mechanically confined within the airframe as it buried itself. The environment of the IJsselmeer acted as a preservation system. Once the wreckage penetrated the silt, it was cut off from the oxygenated water column. In shallow freshwater environments, the greatest threat to aluminum is oxidation and galvanic corrosion fueled by dissolved oxygen and electrolytes. By burying itself in dense, anaerobic mud, the wreckage entered a state of stasis. The sediment sealed the breaks in the fuselage, preventing the intrusion of currents that would otherwise scatter loose items. This geological seal protects not only the metal, but also organic materials. Leather, fabric, and human remains that would decompose rapidly in open water can survive for decades if isolated from oxygen and scavenging aquatic life. For the survey team, the problem was not detection but context. Side-scan sonar could sketch what protruded. A magnetometer could flag steel buried under the mud. Neither could show the fuselage's attitude or the crew stations sealed in clay. The site was preserved and inaccessible. That requirement would define the geometry of the recovery operation. The geometry of the recovery operation was defined by a rigid steel boundary measuring about 35 meters, roughly 115 feet, on each side. To reach the wreckage of Lancaster ED-603, the engineering team could not rely on divers working in the blind. The target area was too large, the sediment too deep, and the visibility too poor for a standard underwater excavation. Instead, the Royal Netherlands Air Force and the contractor Leemans Specialwerken applied the dry polder method, a civil engineering approach designed to create a dry, controlled workspace around the wreck. The primary structure for that isolation was a cofferdam, steel sheet piling driven into the lakebed to form a sealed box. The construction phase began with the arrival of heavy lift barges carrying craning equipment and steel sheet piling. Sheet piles are long, corrugated steel sections with interlocking edges. Using a vibrating hammer suspended from a crane, the operators drove these piles vertically into the lakebed one by one. Each sheet locked into the previous one, forming a watertight continuous wall that penetrated deep into the clay substrate. The result was a sealed steel box rising from the surface of the IJsselmeer, completely surrounding the crash coordinates. Once the perimeter was closed, the team faced the physical governing constraint of the operation: hydrostatic pressure. This is the force exerted by a fluid at rest due to the weight of the water above it. Outside the dam, the lake pressed inward against the steel walls with thousands of tons of force. Inside the dam, as the water level dropped, that counterbalancing pressure disappeared. To prevent the walls from collapsing inward under this differential load, the structure relied on the deep embedment of the piles into the lake bed and an internal bracing frame. The steel walls had to hold back the entire weight of the IJsselmeer while the interior was converted into a dry workspace. Removing the standing water was only the first step. The lake bed itself consists of saturated silt and sand, which can behave like a fluid when disturbed. If heavy equipment cuts into waterlogged mud, the sides can slump and the excavation can refill as groundwater seeps back. To counter that, the engineers used a dewatering and ground stabilization scheme inside the enclosure, a combination of pumping, drainage control, and soil consolidation measures designed to lower pore water pressure and firm up the working surface. The system ran continuously, fighting the natural tendency of water to migrate back through the sediment and keeping the excavation stable enough to support heavy equipment. By September, the cofferdam stood drained, a flat, gray floor of reclaimed clay 13 feet below the surrounding lake. The barrier was no longer water, it was the mud. The separation of forensic evidence from the geological matrix is the operational bottleneck of any recovery project. Once the cofferdam was drained, the floor of the excavation zone presented a uniform surface of gray silt. To the untrained observer, it appeared to be empty mud. To the recovery team from the Bergings- en Identificatiedienst Koninklijke Landmacht, the BIDKL, this clay was a chaotic suspension of aluminum scrap, unexploded ordnance, and biological material. The objective was not to dig a hole, but to filter the entire volume of the crash zone through a fine mesh screen. The excavation followed a strict vertical sequence. Heavy mechanical excavators, operated by the civilian contractor Layman's Specialwerken, removed the non-relevant overburden, the layers of sediment deposited after 1943. As the buckets reached the strata containing the debris field, the pace shifted from industrial removal to surgical extraction. Large structural components, such as the main landing gear legs and the wing spars, were exposed by hand, rigged with lifting slings, and hoisted out by crane. These items confirmed the orientation of the airframe, but they did not contain the primary target of the mission. The search for the missing crew members required a process known as wet sifting. The excavators transferred the debris-laden sludge into hoppers that fed a specialized wash station built on the edge of the dam. This system uses high-pressure water jets to force the sediment across a series of vibrating shaker tables. The physics of the sifting table rely on particle size and density. The pressurized water dissolves the clay bonds and washes the fine silt particles through the mesh, returning them to the lake outside the dam. What remains on the screen is the hard fraction, twisted aluminum fragments, plexiglass, ammunition, and osseous material. This is the catch layer. As the conveyor belt moved the wash material forward, BIDKL specialists visually scanned every square inch. They were looking for objects that did not belong in the geological record, fragments of leather flight gear, parachute silk, or human bone. This manual filter is the only sensor capable of distinguishing between a corroded piece of driftwood and a blackened bone fragment. This phase was governed by a critical safety constraint, the presence of unexploded ordnance. The Lancaster was a weapon system carrying thousands of rounds of .303 ammunition and pyrotechnic signaling devices. After 80 years of immersion, the explosive compounds in these devices can become unstable. An explosive ordnance disposal, or EOD, team supervised every bucket of earth. If a suspicious object was identified, the entire line halted. The item had to be assessed and neutralized before the sifting could resume. This constant interruption created a stop-start rhythm that tested the patience of the crew but ensured the site remained secure. When a relevant biological object was isolated on the belt, it triggered a protocol known as the chain of custody. This concept is the legal backbone of forensic identification. It is not enough to find a bone, the recovery team must prove exactly where it was found and who handled it. Every item was immediately flagged, photographed in situ if possible, and placed in a sealed, evidence-grade container with a unique tracking number. This documentation trail ensures that the physical evidence remains admissible for the final identification process. The chain of custody prevents contamination and guarantees that the remains returned to the families are positively linked to the specific recovery site. By October, hundreds of tons of sediment had been moved and screened, and the site was no longer a place to dig. It was a ledger of what the sort line had captured. What came off the screens would now decide the case. The output of the wash tables provided the definitive answer to the central question of the operation. After weeks of processing the clay matrix, the Royal Netherlands Air Force Salvage and Identification Service confirmed that the search box contained the evidence required to close the case. The recovery team did not find intact bodies waiting in seated positions. The physics of the 1943 impact had precluded that possibility. However, the anaerobic sediment had performed its function. The sifting process yielded specific, identifiable human remains corresponding to all three missing crew members: Pilot Officer Arthur Smart, Pilot Officer Raymond Moore, and Pilot Officer Charles Sprack. The remains and effects came out of the same sealed, oxygen-poor mud that had held the wreck in stasis. Fragments of flight clothing and personal items provided immediate corroboration, while the formal identification process ran its course. The national program's standard is strict. Success means names can be confirmed and returned to families. In this case, the evidence met that standard. In terms of hardware, the excavation recovered approximately 40% of the aircraft. This figure serves as a grim quantifying metric for the violence of the crash. 60% of a 30-ton heavy bomber had disintegrated into fragments too small to be captured by the screens or had been carried away by the currents in 1943 before the silt buried the rest. The recovered material included the heavy steel and iron components that led the descent: the engines, the landing gear struts, and the armored seat pans from the cockpit. The condition of these large artifacts told the story of the terminal event. The propeller blades were bent forward, a specific damage signature indicating that the engines were developing high power at the moment of impact. The structural spars were twisted and sheared, confirming the high-energy entry into the lake. Yet, despite the mechanical destruction, the chemical state of the metal was stable. The aluminum skin sections, once washed of the gray clay, retained their original paint and camouflage patterns. The black undersides of the night bomber scheme were still visible, a testament to the corrosion-inhibiting properties of the dense mud. The recovery of 40% of the airframe presented a secondary logistical challenge. While the human remains were transferred to the forensic laboratory at Soesterberg for final forensic identification, without requiring DNA profiling in this case, the wreckage required disposal or preservation. The engines and landing gear, now exposed to the atmosphere, became instantly vulnerable to rapid oxidation. The team had to transport these heavy loads ashore, keeping them wet or chemically treated to prevent the sudden onset of corrosion that attacks historic aluminum when it dries out. By the end of October, the sifting line fell silent and the search box had been cleared down to sterile lake bed. The three missing airmen were no longer a question in the sediment. They were evidence in state custody, headed into the Commonwealth War Graves Commission's formal record. The operational window on the IJsselmeer is defined by the calendar. By late October, the autumn winds begin to sweep across the open water, generating wave heights that threaten the stability of crane barges and static engineering structures. For the recovery team, this weather constraint imposed a hard deadline. With the sifting complete and the evidence secured, the priority shifted from excavation to demobilization. The steel island that had isolated the crash site for 2 months had to be dismantled before the storms arrived. The restoration of the lake bed required the reversal of the construction sequence. The vibrating hammers which had driven the sheet piling into the clay in August were re-rigged to extract them. As each interlocking steel section was pulled from the sediment, the seal was broken. The waters of the lake, held back by the dam walls, rushed into the excavation zone. Within hours, the dry polder that had exposed the final resting place of Lancaster ED-603 was reclaimed by the IJsselmeer. The site returned to its natural hydrostatic state, indistinguishable from the surrounding water, leaving no physical scar on the landscape. While the site was erased, the recovered hardware entered a critical phase of preservation, known as corrosion inhibition. This process protects the material legacy. After decades submerged in water and silt, aluminum alloys can be chemically stable as long as they remain wet and oxygen poor. But once exposed to air and allowed to dry, corrosion processes accelerate and fragile surfaces can begin to degrade. To prevent that, recovered sections of ED-603 were moved quickly into controlled stabilization, kept wet, rinsed, and placed in treatment tanks. The preservation protocol typically relies on prolonged freshwater bathing to remove soluble contaminants from pores and crevices, followed by protective coatings or passivation treatments that limit oxygen access. The goal is simple: keep the engines and airframe fragments intact as historical evidence rather than letting them deteriorate after surfacing. The biological remains followed a different trajectory. After the forensic verification at the laboratory in Soesterberg, the identity of the 3 missing airmen was formally confirmed. Pilot Officer Arthur Smart, Pilot Officer Raymond Moore, and Pilot Officer Charles Sprack were no longer listed as missing. On October 9, 2025, 82 years after their departure from England, the crew was reunited. The burial ceremony took place at Werkum Spoordijk General Cemetery in the Netherlands. This location already held the graves of 2 of the Lancaster's crew members who had been recovered in 1943. And the new interments reunited the men in one place at last. The interment was conducted with full military honors, attended by surviving relatives who had waited generations for this specific procedural close. The event marked the final transfer of custody from the recovery team to the Commonwealth War Graves Commission. The recovery of Lancaster ED-603 was not a salvage mission in the commercial sense. The value of the operation was not in the scrap aluminum or the restored engines, but in the correction of the historical record. The national program proved that the passage of time does not erode the obligation of the state to its personnel. The engineering resources, the cofferdam, the pumps, the sifting tables, were tools applied to solve a single variable: location. By removing the water and processing the mud, the project converted a probability into a certainty. The lake is quiet again, but the numbers are now correct. 7 men flew the mission, and 7 men are now accounted for.